Hey guys! Oh crap! I copied and pasted this in. Make sure I got everything right. Oh yeah, like this. One minus 150. One minus theta u or v. Okay, sorry. I was copy and pasting that and moving it down. So, okay, in the previous video, this is the third part of the pressure drop in a pat bed reactor video. I just deriving the equation, showing you guys how to work through it. So over here we got, in the last video we did dz. We're trying to turn the Ergun equation from dp dz to dp dw. Okay, so how do we do that? Well, we're going to continue here. So I rewrote the Ergun equation. So you can recognize all this as being constant. The expansion factor is not, the p and the denominator is not, and the t, well in this problem it is a constant, but you can have problems where the temperature is not constant. We'll do with that in future videos. But my point is we can make that B0 because they're all constants. We're going to label them into one constant fudge factor. We have minus here. So the minus is on the outside. So that minus is this minus. Okay, great. Second thing, we got to plug dz in. How do we do that? Well, okay, so we have dp over dz. So plug in this guy. So now we have dp over dw, all in denominator. Make this longer. dw over AC rho c, cross-sectional area, density of the catalyst packing, 1 minus theta. Okay, perfect. And then we have basically negative B0, all of this on the right side. Then we got 1 plus e to the x, p naught over p, t over t naught. That's what we got so far. So we almost did dp dw. We just got to multiply this denominator. Oh, I'm sorry, it's denominator of a denominator. It's actually, you can think of it as being the numerator. So we're going to divide that over to the other side. So we got dp dw equal to negative b naught, 1 plus e to the x, or expansion factor x, p naught p, t naught. As I said, this is the third part of the video, so if you're jumping in just straight from here, I'd recommend going to the first video. All this is explained. Okay, so there we go. And the denominator, we're going to move over AC rho c, 1 minus your void fraction. Okay, so there we are. So now let's look for constants, because we can fudge all the constants into another constant. So what I would do is take your B naught, your AC is a constant, unless the pipe is changing size, rho c, your void fraction is a constant, and everything else is variable. dp dw, negative b, I'm going to say alpha. So negative alpha, 1 plus e to the x, p naught p, t naught. And in isothermal cases, this is going to be equal to 1 because t naught is equal to t. So we can cross out, say 1 in isothermal cases. We're doing just pressure drop, no change in temperature. Okay, so now we got an equation for dp dw equal to negative alpha, 1 plus e to the x, or expansion factor x, p naught over p. Okay, cool. So, yes, and then we also had from the very first video, dx dw equal to, let's take a look. It's been quite a process. This is just a derivation video. This is showing you how the logic flows through dealing with pressure drop. Yeah, there it is. That also, too, is a quite long equation. Sort of. Okay, copy, paste that, bring it down so we can see it here. Turns out we're not going to need to write this part. Okay, so there we go. We got two equations. So what you need to do is first parameterize this equation, right? So we're going to say y is equal to p naught over p, because this is going to make, p over p naught. So when dealing with this will become 1 over y, and this will become just y. Alright? So we're doing with dx dw, dp dw, right? Let's times this by p naught since it's a constant, and then call this p over p naught. Okay? I'm dealing with this equation over here. So then we can say d of y. Okay? You could do that because p is a constant, and the way I did that is you can multiply this one back in and make it back to p. Okay. So now we got y p naught. Divide p naught to the other side. You get negative alpha. 1 plus e to the x. 1 over y. All over p naught, which is a constant which can fold back into your alpha. Right? You can put p naught in alpha. Just call it alpha nu. I don't know. Keep that in there. So basically the whole thing of this video is to get dx dw equal to k cao 1 minus x y. I'm not doing t's anymore. FAO 1 plus e to the x. Okay, so that's your dx dw, and your dy dw is going to be negative alpha nu 1 plus e to the x 1 over y. Then you basically plug in numbers to these two equations, and then you can solve it using an ODE solver. So if you refer to the book, they got methods by which you can deal with non-ODE solving scenarios, like if there's a zero expansion factor. That's another one. So these are good equations to note down. They'll be on your formula sheet. But the whole point of that video was to go through and show you how to derive two equations. Sorry, let me get back to it. Two equations. And then in the following video, what I can do, if you want, is I could do MATLAB solving these two equations simultaneously. But okay, so I hope you guys like these videos, how to get to two equations that you can solve with an ODE solver. Polymath seems to be the biggest one of choice, at least with the book. But that's how you break them down. You know, this is how you get from the Ergun equation to the dp/dw. This is how you get from the material balance to dx dw. And on an exam, they're not going to have you do this. So that's why I'm not going to go forth with any more theory. I figured that was a good introduction. But in a testing environment, you can't use a computer, so therefore you can't use an ODE solver. So this is only something you're going to see on your homework, this ODE solving stuff right here. So reference into Polymath or MATLAB. Okay. I might do a video in the future on how to solve two differential equations simultaneously on MATLAB. Alright guys, hope you enjoyed it. Let me know what you think in the comments.